Yes, it's great. For the last talk today, we have Julius Marx talking about certified RISC-V interpreter. So it's really nice that we are covering all those different topics, going from topology to probability and now really actual computer stuff. So let's enjoy that last topic for today.
Yeah, thank you very much. Welcome to my presentation. My name is Julius. I'm a PhD student at the Hochschule Rhein-Main, the University of Applied Sciences in Wiesbaden. And I'm going to present you MRiscX, a certified RISC-V interpreter with Hoare logic as DSL and lean. First of all, as a little forward, this presentation is going to be about a presentation of MRiscX and how you can use it. The exact details about the implementation and how we certified the interpreter and the machine state model. I'm going to leave out because of time reasons. But if you're interested in that, we plan to make some publications about it, and you can always get in touch with me. My email address is on the last slide. Let's start with the motivation of the project. Why do we want to formally verify assembly code? So we know that writing assembly code is quite common in certain areas of computer science. If you want to write a device driver, or in the area of cryptography, if you want to prevent certain attack patterns, you need to write the assembly code directly. And also, sometimes it is necessary to review compiled code. For example, if you work in the cryptography you want to review an implementation of an algorithm, or in the reverse engineering context, and also if you just have no trust in the compiler. So we see there are quite some use cases why you want to actually verify the assembly code directly. Next, I'm going to explain some fundamentals so that everyone here should be able to follow this talk. Let's start with RISC-V. What is RISC-V? RISC-V stands for Reduced Instruction Set Computers version 5. It's an open source instruction set architecture and was originally designed to support research and education. By the time it gained a pretty huge popularity in the field of embedded systems due to its modularity, the extensibility, and also the factor that it is open source plays a big role here. It provides an assembly language for creating object code, and I've brought a small example for that. It is not necessary that everyone understands what is going on here in detail. By the way, can you see my cursor? Okay, I hope you can see my cursor. We see that there are two labels in here, the label _start and the label finish. And these labels wrap up some instructions. For example, the load immediate instruction here, which loads the value 13 into the register T0. There's also some XOR operation going on here. But just that you have an idea how this RISC-V code can look like. Next, I'm going to define two paradigms, the structured and the unstructured programming, because I'm going to use those terms in the next few slides. Structured programming essentially means programming that does not use goto, and on the opposite, unstructured programming does use goto. Let's get started with the Hoare logic. The Hoare logic is a formal system for verifying the correctness of structured and imperative programs. The goal is to formulate and prove statements about these programs. And for that, we can use the Hoare triples, which is a pretty central element in the Hoare logic. Again, here we have a small example. We can see P and Q inside the curly braces, where P is a precondition and Q is a postcondition. And in between those, we see the S, which stands for a code or a program. And this Hoare triple means if we know that the precondition P is true and the code S executes, then we know that Q must be true as well. So a little example for that. If we know that the value X holds the variable X holds the value 0, and we know that the code X is defined as X plus 1 is executed, then we know that the variable X holds the value 1. So you can use this Hoare logic to specify your implementation or your code. And to actually prove the correctness of this implementation, you can use the Hoare rules. I'm not going to explain every Hoare rule right now because we don't have the time for that, unfortunately. But one rule is actually pretty important, so I'm going to explain it. And that is the rule of composition. This rule is used quite frequently. And yeah, you can see this horizontal line and everything above the horizontal line are the preconditions to be able to apply this rule, and everything underneath is the effect of the rule. And we can see if we have two Hoare triples, where the one Hoare triple has the same postcondition as the other Hoare triple has the as precondition, sorry. So if one Hoare triple has the postcondition R and the other triple has the precondition R, then we can merge these two Hoare triples together and get rid of this R, have the program S1 and the program S2 just merge together and execute it sequentially. And we can hold on the precondition P and postcondition Q. Now I've said that the Hoare logic is implemented for or invented for structured programming, but we do know that assembly languages are unstructured. So we've decided to use a Hoare-style program logic, LAS, from Lundberg et al. And this Hoare-style program logic is an extension of the Hoare logic. It introduces a program counter as well as a white and black list into the Hoare triple. So we can see like a new notation down here. Again, we have P and Q as pre and post condition, but in between those we see L as a line on where the program counter points to before executing a program, and then the white and the black list. The white list is a set of lines, and it contains any line where the program counter might point to after successfully terminating the program. And the blacklist holds any line which must not be visited during the runtime. So you can think of it like that. Without the black and white list, we could not ensure that we just visited the lines we are inspecting. We could not be certain that maybe the program jumps to any other line, or that we jump from anywhere else into this program. But with the introduction of the black and white list, we can actually ensure that we just visit the lines we are inspecting. This extension of the Hoare logic also provides a lot of Hoare rules. But they essentially mean, or they have the same meaning like the Hoare rules from the conventional Hoare logic. We have this S sequence rule, which is the rule of composition. The extension or the extension LAS adds 3 more Hoare rules, which allow modification of the black and white list during proof of correctness. All right, and now we can see what a Hoare triple looks like in the DSL we've implemented, which we called MRiscX. We can see in the first 3 lines we introduced some variables. They are from of type UN64 or set UN64. Then we can see the keywords MRiscX and the keyword end. And in between those two keywords, we can write the RISC-V assembly code. So yeah, we see a label main, a label, some label, um, and with some instructions. And then in the last line, we see the actual Hoare triple. So we have the pre and post condition inside these doubled curly braces. We've decided to change from the squared bracket to those doubled curly braces because the squared brackets are used for this, and to avoid any parsing errors, we used these um, doubled curly braces. And then we have the L and the whitelist and the blacklist. All right, and now I want to present you how you can actually use MRiscX to provide formal verification of your RISC-V code. So first of all, in the next few slides, I'm going to use those characters, but they actually mean these Unicode characters, yeah, just for your information. So now, how do I define a specification for an implementation in MRiscX? As we've seen, we have in these doubled curly braces the pre and post condition, which are terms of type proposition. So we can use any term you could write in Lean. Additionally, I implemented some custom terms for assertions about the machine state. So for example, we have a terminated within these doubled parentheses. And yeah, this is an assertion about the terminated flag. This terminated flag indicates whether a machine state is in a legal state or not. So if this terminated flag is true, then the machine state is in an illegal state and it won't execute any instruction anymore. And so if it is false, everything is fine and the next instruction can be executed. Then we have this X with some squared brackets where you can write either a number or an identifier into. And this represents any kind of register. In this case, we only have register called X, but yeah. Then we have, then you can make assertions about the memory, about the labels, and about the program counter as PC inside these doubled parentheses again. Here are some examples of legal pre and post conditions. The first one is like the weakest precondition, which is just true. The second one is a pretty common precondition because we need to make sure that this terminated flag actually is false to ensure that the next instruction can be executed. So this, we almost always need this as a precondition. And then we have some random pre or post condition where we make assertions about the registers, or in the last picture, we can see some assertions about labels, that some label is present and it is present at a certain line, or that the memory holds a certain value, which is calculated by an XOR operation. Just some examples. So now we have our specification of our code, and in the next step, we want to actually verify the correctness of this code. How can we do this? Well, I've already mentioned that we can apply Hoare rules. We can also use the specification of instruction. We've implemented them, so you can use them for the proofs. And also, I've implemented some custom tactics for proof automation. For example, there are multiple ways to apply the rule of composition, or S sequence, as it is called in the extension of the Hoare logic. yeah, then there's a custom tactic to apply a specification, and also there's some proof automation tactic which is called auto sequence. When the time is enough, I can maybe show that in a live demo what that actually does. All right. Now I've brought a little example for a Hoare triple, which we yeah proved the correctness of. So we yeah we can see again in between this MRiscX and this and the RISC-V code, and this is an implementation of the one-time pad. It is like separated into two main parts. The first one is the part with the label main, or within the label main. Here we can see that the addresses of the plaintext P, the key in K, and the ciphertext in C are loaded into some registers, and the length of each is loaded into into the register X3. And then after that, we have a loop. This loop is the actual encryption of the plain text with the key. We can see that we have a conditioned jump in the first line of the label loop. And in the last line, we can see we jump back to the label. And in between happens the encryption, which is not too interesting for now. Then after the keyword end, we can see that the Hoare triple begins. Yeah, the first and most important precondition is the not terminated, I've explained. Then we have some assertions about the addresses of the plaintext, the key, and the ciphertext. We have to assure that they don't overlap each other. And also we have to make sure that there's no overflow happening. Then we can see where the program counter points to, and in this case, it is the label main or the first instruction of the label main. You can see that it is okay to write out the label main names. Then we want to finish when the program counter points to the label finish, and we do not want to visit any line which is greater than finish, or the first instruction of the label main. This might be a little bit confusing, but the Hoare-style logic LAS from Lundbeck et al. Only considers machine states after the first instruction is executed. So by adding the first instruction of the label main into the blacklist, we can assure that after the first instruction is executed, we did not visit the first line of the main label again. The post condition here is a assertion that every every character in the plain text was correctly encrypted with a key and is stored in the memory where we wanted, or the memory we allocated for the ciphertext. All right, so how can we now use the tools I've just presented to actually go through this implementation and verify the correctness? Well, I've presented the rule of composition, and this comes in pretty handy in here because we prove from bottom to top. So we can apply this rule to the Hoare triple, and instead of merging two Hoare triples together, we can split up one Hoare triple into two because we are proving from bottom to top. And by applying the rule, we can make a cut between the main and the loop label. And therefore, we now have the two Hoare triples we can look at separately, which makes things easier. Then let's start with our first Hoare triple, which is essentially the label main, where the um, addresses and the value L are loaded into the registers. And here we can now again use the rule of composition to again split this Hoare triple into two. We can like peel off the last instruction and therefore isolate this last instruction. Now we have, and now what we've achieved, we only have to show what this instruction is doing, and we only need to show that this instruction is kind of working correctly. And for that, we can apply the specification of this instruction, which you can see here, with the tactic apply spec. We can apply the specification of the instruction load immediate. We need to provide some values, for example, where the program counter currently points to, the register which is being modified, and the value we want to load into the register. But after applying this specification, this second Hoare triple is proven correct, and we can go on with the first Hoare triple. And I think you get the point. We can repeat this process until we've inspected each instruction separately. And yeah, by doing so, we can proving that this label or this part of the implementation is actually correct. Now we want to have a look at the loop section, but because the time is pretty, I'm running out of time. I'm going to go over it pretty fast, not in detail, but essentially what we're doing here is we apply another Hoare rule. This is the rule as loop, or the rule of iteration. And for this, we need to think of a condition for the loop, a loop invariant, and a loop variant. The condition is already given, but we have to think about an invariant and about a variant. And once we've achieved that, once we found those, we can write them down and then go on with two Hoare triples. And the first one is when we are actually kind of going through the loop body. And in this case, we can again apply the rule of composition. We can isolate each instruction and repeat the process. And therefore, we can prove that the loop body is working correctly. And then we have to verify that we are actually jumping out of the loop once the condition is not true anymore, which can also be done by applying the specification of the branch equals 0 instruction. And after that, we are done, and we've shown that the implementation of the one-time pad is actually working correctly. All right. The last thing I want to do is give a little outlook. What might be the next steps? Well, we want to complete the assembly commands. At the moment, there are some assembly commands missing. We've just implemented all the commands we needed to implement the one-time pad and some more, but there are definitely some missing we want to implement. Then we want to incorporate calling conventions of RISC-V. As you've seen, it was possible to modify the value of the register X0, which is not possible in RISC-V. There, the register X0 is hardwired to the 0. This kind of stuff we want to implement as well. Also, we want multiple register names and go further with the proof automation. yeah, there are many different approaches we can go. For example, proof automate the application of every Hoare rule, not just the sequence application, or the application of the specification. As you've seen, it was necessary to provide some values which can be calculated, or they are already present. They just need to be extracted from the goal. And there we want to kind of incorporate multiple stages of proof automation, how much you actually have to write down. Also, currently a detailed documentation is work in progress, and yeah, there might be some steps we didn't think of yet, or some projects we maybe are created. All right, those were my sources, and I thank you for your attention, and I'm looking forward for any questions.